Well, hello everyone, welcome back to Dprieto TV and happy Thanksgiving weekend. I hope you had a fantastic Thanksgiving if you're watching this in the United States. Oh yeah, hope you had an amazing Thanksgiving. We are back with Prietology, back-to-back episodes for the first time in what seems like a long time. We haven't done back-to-back Prietology episodes in a long time, but yeah, we are continuing talking about stars. Like I said last time, we talked about the beginning of stars and how they're born. This time we'll talk about what happens near the end of their lives, not just when they die, but the whole process of how they get to the end of their lives. Get excited for this. A stellar explosion is imminent for today. So yeah, let's waste no more time and yeah, let's go over key terms. And we got some announcements at the end. Alright, we got the same amount of terms as we had last week. We got 8 terms. And like I said, we're talking about the stars at the end of their life. And specifically, I mentioned a word called supernovas last time. Right here. So along with supernovas in our stellar explosion today, Sirius, Betelgeuse, Cat's Eye Nebula, White Dwarf, Supernova, Neutron Star, Black Hole, and Supernova Remnants. So yeah, let's waste no more time. Let us begin. Alright, first term. So along with talking about what happens at the end of the life of the stars, we get to talk about 2 more stars that are interesting, plus a nebula that is also interesting as well. So yeah, here's another star that's out there somewhere in the universe. Well, we know where it is. Sirius. It is the brightest star in the night sky. It's known as the Dog Star and is located in the constellation Canis Major, which is the big dog. There's the Canis Minor, which is the little dog. So yeah, it's a double star system that is roughly 8.6 light years away. So as you can see, now that we're talking about stars and other astronomical objects, we're going to start talking in terms of light years. Light years are massive amounts of time, millions of miles, millions and billions of miles. So yeah, 8.6 light years away, the double star system made up of Sirius A and Sirius B. Both of them orbit each other, so it's kind of like they're spinning around, orbiting each other. So yeah, Sirius A is the bigger and brighter star, and Sirius B, which is called the pup, like a puppy, is a smaller and dimmer star called a white dwarf. Like, remember last episode how a lot of these terms were intertwined with each other. It's going to be the same for this one. This is actually part of a Greek myth. It's the Greek myth of Sirius, which is believed to be a 2-headed dog. It's believed to be the hot day, the beginning of hot days, the beginning of the sweltering heat in ancient Greece, which, dog days. That is where that term derives from. It derives from Sirius, the dog days, the hot and humid and horribly hot, sweaty days. When people saw this star, people were just like, oh no, the big hot days are going to start coming. And maybe yeah. Fun fact, I actually kind of mentioned it. Sirius is a 2-headed dog. So that is the myth of Sirius. As you can see there, it's a 2-headed dog. Yeah, so that's what the Greeks believe, that this is the beginning of their hot weather back in ancient Greece. This is an interesting one to pronounce. Beetlejuice, like the musical? Is it a musical? Yeah, like there's a musical called Beetlejuice about like a guy who's green. I don't know. I've never seen it. It's the second brightest star in the night sky and is located in the Orion constellation. Orion is probably the most famous of all constellations. Orion the hunter with his shield and sword. Pretty interesting. A red supergiant. So it's one of the biggest in the universe. Remember we learned last time that these supergiants are massive, they're ginormous objects. The biggest star that can emerge from a starburst nebula. It's a red supergiant, and like I said, it's one of the biggest known in the super system, and is very, 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 very hot. Average temperature is 6,500 degrees, so it is boiling hot. It is scalding. It is absolutely infernally hot. It'll burn you in an instant. Yeah. So, and because of its very hot temperature, it's kind of a bit of a paradox with this next one. Because of its super hot and red hot temperatures, literally red hot, we can see that it's near the end of its life. But Betelgeuse is a relatively very young star with only a life of 10 million years in astronomical terms. That is very short, very young. So Betelgeuse might not live that long of a life, considering a lot of these stars. Remember, like we learned last time, super heavies don't live very long lives because they consume so much hydrogen, so many elements around them. They take a lot to continue their nuclear reaction. So yeah. So what happens with Betelgeuse and stars like Betelgeuse and other supergiants, when these big supergiants start running out of hydrogen, when they start running out of hydrogen, which is kind of like the fuel for their nuclear reactions, sun-like stars, stars like that we have like our sun, they usually die. And then we'll talk about how they die in a bit. But yeah, sun-like stars like our sun and was it Alpha Centauri? I believe so. Yeah, Alpha Centauri A and B. When those sun-like stars start losing their hydrogen, they die. But supergiants can start using their supply of helium. So yeah, that hydrogen and helium, they still have an extra reservoir that compared to suns that don't, compared to sun-like stars that don't have enough. But yeah, fun fact, like I said, Betelgeuse is near the end of its life. So the eventual supernova, which we'll talk about, what happens at the end, the eventual supernova, the explosion of when it dies, will be brighter than the moon in daylight. It is going to be huge. You can even see it at night. It might be as bright as a full moon at night. That is how bright the supernova of Betelgeuse will be. So when it explodes, maybe in the next 100 maybe years, tens of years, maybe billions of years, keep an eye, because it's going to be a pretty interesting astronomical event. So yeah, here's a good feline friend, but a good feline friend that would take you millions and millions of years to get to. Cat's Eye Nebula. Not the cat eyes nebula, the cat's eye, like your eye. A Cat's Eye Nebula. Well, not a Cat's Eye Nebula, the Cat's Eye Nebula. It's a place in the universe that is a planetary nebula that is located in the Draco constellation, or Draco I think, which is the dragon. Here's Draco. As you can see, it's in the shape of a dragon. It has a dying star at its center, and it is 3,300 light years away, so you are not getting there anytime soon. It has a dying star at its center, and the shape of it, considering how the Cat's Eye Nebula looks, this is the Cat's Eye Nebula. That is what it looks like, and the shape of it could possibly signify that they have a double star system, kind of like what we saw with Alpha Centauri or Sirius. Both of them have double stars that are orbiting each other. So, how these Cat's Eye Nebulae forms, or planetary nebulas, that's what they're called. Fun fact about the Cat's Eye Nebula, remember how I said that radiation circling all those circling gas clouds? They are not slow at all. Those clouds are massively fast. 62,000 miles an hour winds are in the nebula, and they're concentric, which means they have the same center. So, what's an example of concentric? Our magnetic field. So you know how our Earth, let's say our Earth is right here. Our magnetic fields go like that. So the winds around the Cat's Eye Nebula, because it's all swirling gas, they circle around the nebula and they have the same center, which means concentric. So it's not that friendly of a place, even though it has a pretty nice name. Like I said in the last term, these next 5 terms, white dwarf, supernova, neutron star, black hole, and supernova remnant, are all interlocked with each other. Let's start with our first one. We mentioned this in the last one with the Cat's Eye Nebula, the white dwarf. We've talked about red dwarfs, brown dwarfs, yellow dwarfs like our sun. White dwarf time. It's a star that has the same mass as the sun, but has no gas, no fuel, it's dying, and it has no fuel for those nuclear reactions, those essential nuclear reactions that all stars need. So, that means, with no nuclear reactions, it's just a cold ball in space. So, that makes it one of the most dense things in the universe. It is super dense. I'll tell you how dense it is in our fun fact. It's scalding hot at first, so like we saw in the Cat's Eye Nebula, that dying star in the middle is dying out. So it's scalding hot at first, but then it fades to just a cold, dead, lumpless form. It's a star, but just cold and fades out, and yeah, that's how these white dwarfs usually end their lives. This is a white dwarf star. As you can see, it's all cold, dim, it's fading out, and yeah, it's not going to have a very long life for long as it fades into nothingness. This is usually, like I said, the remnants of a giant star. So, like I said, one time, like we said, in the Cat's Eye Nebula, there was a red supergiant that creates all those glowing colors, and that red supergiant is fading into a white dwarf. So once those red supergiants or supergiants use all of their fuel, they fade into white dwarfs. They start losing all their fuel, their energy, and they just get dimmer and dimmer and cold. They get dimmer. It gets colder and colder and colder, and that means it doesn't even have enough energy to fall under its own gravity, make a supernova, so it collapses on itself, so it just gets like squished down and starts breaking apart, and it becomes denser and denser and denser and denser and denser, because all that matter from the star is getting compacted. It's getting super compacted, it denses and crumples into a ball. That is what makes white dwarfs the most dense thing in the universe. Not the densest, but one of the most dense things in the universe. Fun fact about white dwarfs, a single teaspoon a white dwarf star material. So if you go to a white dwarf, which I don't think you can right now, but if you go to a white dwarf and you take a teaspoon out of it, that teaspoon can weigh as much as a 4x4 car. So your average car, your average minivan car, 1 teaspoon of a white dwarf star is about the weight of that. So imagine trying to pick that up with a spoon on Earth. It is super dense and super heavy. It is absolutely dense, but it's all dead. It's all dead matter from this star that makes it so dense and as it collapses on itself. Alright, so now that we've talked about white dwarfs, let me move to this side. This is a term that we've mentioned already a good amount lately, supernova. This is a term we've been building up to. This is the stellar explosion. This is the thing that our episode is named out of. The stellar explosion. A supernova, and it happens when a supergiant dies it's so powerful that it can create star formations and nearby starburst nebulae. So it is so powerful, essentially, a supergiant just literally explodes. It just destroys itself. It implodes and it sends all the matter everywhere for light years, and it happens like that. It's super quick, and it just sends all the matter and particles and all its light everywhere. It's a giant, astronomically sized space explosion. Yeah. The leftover core that is left, so not all of the star gets destroyed, but the leftover core from a supernova can create either a neutron star or a black hole, which we will also talk about. So get excited for that. It happens when a giant star runs out of fuel for its nuclear reactions, and these supernovas can be almost 500 times brighter than the sun. So these are ginormously bright. Like I said with Betelgeuse, when it eventually enters its supernova phase, it can be as bright as the moon in nighttime, a full moon in nighttime. So I'm telling you, these supernovas are massively big. Get excited for when Betelgeuse explodes, if it explodes in our lifetime. So yeah, like I said, this is when stars run out of their fuel for nuclear reactions, and this happens, so let's get our physics in. So you have your force of gravity of these stars. It happens, supernovas, when the force of gravity caused by the star's mass overpowers all of the repelling interatomic forces. If you go back to, I forget what episode it is, but if you go back to season 2, card up here, if you go back to season 2, and I believe it's episode 4? Yes, it is episode 4, season 2, episode 4, when we talk about strong force, weak force, nuclear forces, or strong internuclear forces that hold our atoms together. So it's when the star's mass overpowers all that strong nuclear forces holding all the atoms together. It causes to collapse on its own gravity and just explode, expelling all of its matter everywhere. Fun fact, you know how I said it happens like that? The core's collapsing speed can get up to 43,500 miles per second. It is rapidly quick. These explosions are hugely fast. So yeah, the core just collapses on itself, and once the star's mass overpowers the intermolecular forces, it blows up, and it's never seen again. So, neutron stars. Like I said, these are the remnants of, it depends on the size of the star, but it's the remnants of a supernova. This is the leftover core after supernova that has a solid crust of iron that makes a very small star and weighs more than the sun. So, it's pretty heavy, these neutron stars, because it's all the leftover core. So, pretty heavy stars. They are technically stars, but that doesn't mean there's a star inside a star. No, these are formed after the leftover core and all the matter just gets exploded out by a supernova. These have about usually a diameter of 6 to 12 miles, so it's pretty small. Only stars that weigh between 1.4 and 3 suns wide, so our star would create usually a nebula or a supernova, which would incinerate us all once it explodes. So it weighs between 1.4 to 3 suns, and so stars that weigh between 1.4 and 3 suns create neutron stars. Because of its unique characteristics of its very heavy density, and because it's very small, to escape its gravity you have to reach half the speed of light. The speed of light is 300 million meters per second, so it's incredibly fast. I don't know what that is in miles per hour, but you have to have a very, 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 very fast speed if you're going near a neutron star, because otherwise you are going to get pulled into its gravity, because it's so dense. It's the core of a leftover star, so you can imagine these are pretty interesting things. This is a neutron star, as you can see, pretty small, but at the same time still kind of has some of those star properties that you would usually see in your other stars. Very kind of bright, but not the brightest star out there, not the most spectacular looking star like a supergiant. Along with having a very strong gravity, it has a very fast spin. It spins one rotation around a second. So very, very, very fast compared to Jupiter that has an average day of 10 hours, which is also very fast for a planet. But yeah, neutron stars, very fast spinners, and is made of the neutrons. Why it's called a neutron star? It's made of the neutrons that form when electrons and protons, in a supergiant, join together. So, as you know, our nuclear reactions that are occurring in the core of our stars, protons and the electrons join together, and the leftover neutrons, because those protons and electrons get exploded out from the supernova, the leftover neutrons is the thing that makes our neutron stars. Some neutron stars can make beeping sounds, like literally beeping sounds, can literally pulse like this and be like beep, 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 and they can be detected on computers, and the beeping stars that can be detected on a computer and that pulse out like this, those are called pulsars. That is where that term comes from, and that pulsar is coming from a neutron star. Fun fact, there are over 2,000 neutron stars in the Milky Way, so there's about averagely, well actually not that averagely because there's trillions of stars in our Milky Way, so it's not that big of a thing, but there's over 2,000 stars, so there's about over 2,000 stars that are 1.4 to 3 suns big. So yeah, neutron stars, not that much of a rarity, but also, they're a bit of a rarity, but not that rare to find as well in our Milky Way. Ooh boy, oh boy, what a term. I remember when we were finishing up season 4, and I announced that we were doing astronomy, this was going to be one of the highlight terms of the season. Black holes, the endless mystery of space. No one knows what really they are. They're just things in space, but what we do know is that it's a mysterious hole in the fabric of space that only forms from, remember, from our supernovas. They can either have two consequences. They can form a neutron star or a black hole. So, when these stars explode, they can either make a black hole, which can only be made by stars 3 times heavier than the sun. So our sun needs to be 3 times heavier to be able to form a black hole. So, don't worry, the sun will not form a black hole when it eventually explodes, but that doesn't mean it won't be painful for us on Earth. Because they give off no radiation whatsoever, no light radiation, they can stay hidden because they're literally black in the fabric of space, and they can warp space-time, which is something we'll talk about because space-time is a weird concept. We'll say that for the end of the season. So yeah, they can stay hidden, they warp space-time, they absorb all types of radiation, you can swallow whole stars, they can swallow up, not galaxies are a bit too big, but they can swallow whole stars, they can eat light, not even light can escape its grasp, its pull. Its gravity is astronomically huge and sucks up anything in its path because of the stars, because of the massive amount of these stars, the mass of these stars. Black holes can suck up anything that goes in their path, even light. We have no idea where they go. They go to some endless point. They shrink down like a funnel. They get thinner and thinner and thinner and thinner and thinner and thinner until they shrink into a point, an infinitely small point, which is called spaghettification, or being spaghettified. As you know, spaghetti is a noodle, it's a very long noodle, so essentially if you were to fall inside a black hole, you would get stretched out even thinner and thinner and thinner until you are as thin as an infinitely small point, as you're broken down into your smallest subatomic particles until it is exactly the thickness of an infinitely small point. Not a very favorable death. You don't want to be sucked into a black hole because I don't know about you, but I don't want to be broken apart into subatomic particles and thinned down to the thinness of an infinitely small point. So yeah, doesn't sound fun. The temperature of these black holes, fun fact, is about 80 million degrees Fahrenheit. So that doesn't mean because they're very black and they don't let off any radiation doesn't mean they're cold. No, they are very hot. Remember, they are the leftovers of these supernovas. So they are boiling hot. Yeah. Alright. One final term to go. I'll go on this side. Yeah. One final term to go here in episode 5 of season 5. Yeah. Supernova remnant, or supernova remnants, however you like your words, plural or singular, is the remains of a supernova explosion that is essentially, like, you know, you have your core, all that stuff that gets exploded out, That's this. It's the formal term for it. Supernova remnant, all that matter, all that dust, gas are the major sources of cosmic rays in the Milky Way. So we have our Milky Way. A lot of the cosmic rays and radiation that comes from the supernova remnants. All that matter, that is really the explosion part. So if we take a picture here of a supernova, all that explosion part, those are supernova remnants. There are particles of dust, gas, matter, elements, metals that are exploded by this at searing hot temperatures that are emitted by these supernova remnants. As the star explodes, they can travel up to speeds of 62 million miles per hour during the explosion, during the supernova phase, as they explode out 62 million miles, 6.2 million miles per hour. That is lightning fast, even faster than lightning, like that quick. It's in an instant a supernova becomes a supernova. Yeah, it's amazingly fast and super cool to see. The superheated gas, like I said, the super boiling, scaldingly hot gas that's millions of degrees from these supernovas, can emit X-rays, cosmic rays, gamma rays, ultraviolet, every single type of deadly radiation you could think of comes from these supernova remnants. Cosmic rays, like I said, the major source of these cosmic rays in the Milky Way come from supernova remnants, which can make them look like thunderstorms as they cool down. They can make them look like thunderstorms with lightning and stuff like that, and make them look cool colors like you saw in the supernova. It looks nice, a lot of pretty colors, a lot of pinks and greens and blues. They're all the exciting of those molecules like I talked about when we talked about, it was the Cat's Eye Nebula. All the exciting of molecules creates those cool colors of supernova remnants. Like I said, they're exploded out. They can consist of carbon, oxygen, sodium, magnesium, sulfur, and iron. All of those are life-sustaining elements. So they could possibly bring life to some planets, so who knows? Maybe supernova remnants are the key to discovering life. Final fun fact, the average weight of supernova remnant material, so if you take a bucket of supernova, come on. Let's say you have a star, it explodes, it can turn into a supernova. All that supernova remnant material, if you were to gather that all up into a bucket, it would weigh about 1 times 10 to the 28 tons. So 1 followed by 28 zeros, which is about 10 non-million. Alright, that's the end. Let's go over announcements as we end this episode. What an interesting episode. Now we're done talking about stars. We've talked about the birth of stars and all the stuff that happens after they die. I've honestly got to say, all the stuff that happens after they die is pretty interesting. I think it's more exciting than the birth of stars. But yeah, that's 2 episodes of Stars back to back that you're done. We are done talking about stars, and we are done with Season 5, Episode 5. What another episode this was, or 2 episodes this was. I hope you enjoyed it. Announcements times. One thing I've decided over the past couple of years, that the credits that we have, they're kind of outdated, as you can see. They're kind of outdated. That's a picture of me from 2019, so it's 2023. It's a bit outdated. Next year we will have new credits, so get excited for that. Next video, that surprise game I told you about, that Pac-Man game, that antique Pac-Man game, we are playing it next time out. Like I said, this past week was Thanksgiving, so I hope you had an amazing Thanksgiving if you were watching this in the US, or if you're from the US, happy Thanksgiving, happy late Thanksgiving. But next time we are playing Pac-Man coming on December 10th, so get excited for that. New Pac-Man game, December 10th, and after that we have another Prietology, and then the Christmas special, which I've decided what we're doing this year. It's going to be pretty special. Get excited for that. So enjoy that. Coming on December 10th. So that'll be the next video. But the next episode topic, I don't know when the next episode is, but it's the 2 weeks after the Pac-Man video. Next episode topic will be about, we're getting even bigger than stars, galaxies. We are going to start talking about galaxies. We have 2 episodes on galaxies. All galaxies. We're going to start talking about galaxies. Yeah. Get excited. We've got some interesting stuff here in Season 5. But yeah, thanks for watching. I will see you in 2 weeks for our new gaming video in Pac-Man. See ya. And remote.